All right. Good evening, everyone. Let's start. So today we're going to talk about membrane separation. We have just covered standard filtration. Membrane separation is somehow similar to standard filtration, but membrane separation has its own characteristics. So later, you will understand that when we talk about membrane separation, it's actually very complicated. Okay, you have a lot of separation types under membrane separation. Okay, so membrane separation is a very broad concept, and also membrane separation is used not only for water treatment, but for other separation. Right? So separation is a very important industry in many different industries, like petrochemical purification, drug purification, etc. Of course, membrane separation becomes more and more important and widely used in water or wastewater treatment. Okay, especially if you want to maintain very good water quality. Okay, very good water quality. When we talk about future water treatment plants, in many cases we're talking about membrane separation based water treatment plants. Right. And so not only ultrafiltration, but also nanofiltration are anticipated to be widely used in future water treatment plants. So what is membrane separation? So what is a membrane basically? Separation, so perhaps everyone understands, right? Separation, separate A from B, that's separation. But what is a membrane? You probably have heard this word before. We know that we have biological membrane, okay? And biological membrane can perform a very dedicated function. So the best membrane we can make now cannot mimic what biological membrane does. Right? So very complicated and very interesting properties. Actually, we're learning from biological membrane. For example, biological membrane contains some special protein, which is called aquaporin. Right? So you can transport water molecules very fast, and we want to make that type of protein and use them in, say, water purification. Right? So we're learning from nature, but we cannot even, still we are very far from, okay, from the natural system. But basically, membrane is a thin barrier or film. Okay, it needs to be thin, right? And when you think about standard filtration, we talked about last lecture, right? So it's very deep, 2 or 3 meter in depth. But when we look at the thickness, I have a few samples here. It's very thin, okay, millimeter probably in thickness. When we look at the selective layer, it's even thinner, okay? Hundreds of nanometer in thickness. So it's a super thin, thin barrier or film placed between 2 phases. In our case, we talk about water, right? Water and water. But in some cases, you have gas, right? Gas and gas. Selectively permeable to certain species. Selective means some can pass through, some cannot. All right. It's a separation technology. And for anthropogenic membrane, we need to apply a driving force. The driving force could be concentration, right? Concentration, diffusion driving. Could be pressure, and pressure is the most common we use in water treatment, right? From less than 1 bar to dozens of bar. Nowadays we have ultra high pressure. The pressure could reach 120. Right, so it's very high pressure. And temperature driving, okay, like membrane distillation, the driving force is temperature, like heat, right? So during that process, you convert liquid into gas first, or vapor first, and then separate the vapor, or electrical gradient. Okay, that can be applied in the separating of charged species, right? So charged species move in an electrical field. But anyway, generally we have to apply a driving force, okay, driving force. And this is a very simple scheme. You see that there are some pores, right? Some pores, and we have the solutes, we have the here water molecules, right? Water molecules. And this is a very ideal scenario, right? We have seen this 100% rejection or 100% being retained for the solute. But in reality, we cannot have this perfect pores, right? They have a distribution, and in many cases, you cannot achieve 100% retention. Probably 99, 95, etc. Pressure difference, like in water filtration, right? We have microfiltration, ultra, nano, and reverse osmosis. These 4 are the common types. We're going to discuss the details of each separation scheme. Chemical potential, like dialysis, gas separation, etc. Electrical dialysis, right? Electrical dialysis. You have 2 electrodes. Between the 2 electrodes, you have a membrane, right? Membrane. And temperature difference, membrane distillation. Okay. And different membranes have different applications. Therefore, we say that membrane separation is a very broad concept. Okay. For example, membrane distillation, perhaps you use it for the treatment of very high salinity wastewater, right? So how much high? So perhaps 3 times salty than seawater. Okay. When the water contains that high concentration of salts, you can barely use pressure driving separation. Later we will learn why we cannot use membrane separation. Okay. So there we use temperature driving, like membrane distillation. All right. So we say that membrane is a thin barrier or film, right? So they're made of different materials. The most common is polymer, right? So here You can pass it around and you can open it. We have different pieces. We have flat sheet. We have hollow fiber. Most common material is polymer, right? Different polymer because they can be cast into different shapes, right? They can be functionized easily. They are relatively cheap. So probably the most common material, polymers. And we have ceramic, and ceramic becomes more and more popular because it's tough, right? It can be resistant to high pH conditions or low pH conditions, right? So it can last for a long time, right? But the membrane, it's kind of difficult to make ceramic membranes, especially when you want to control the pore of the membrane. So it's much easier for us to do that for polymeric membranes. So interestingly, we have some metal membranes as well, right? Metal membranes. So you can think metal-based membranes are expensive, right? Expensive, like aluminum oxide. But you can make them with very uniform pores, so they can do very special separation. They can be used in certain unique fields. We could also have liquid membrane as well. Imagine you have viscous liquid, right? When you apply some pressure, the liquid film actually will form certain pores, and that pore could be used for separation, right? When we talk about membrane structure, we have this symmetric. What does symmetric mean? It's a concept based on the depth. Along the depth, it's uniform, right? It's uniform, so it's symmetric. Look at the scheme, symmetric or asymmetric. What does asymmetric mean? You have a very dense layer at the top, right? You have porous layer at the bottom, which acts as the support. So it's asymmetric, right? Asymmetric. They can be integrated, right? So the whole membrane is made of the same material, or they can be composite, right? Different materials, layer on top of another layer, right? So we have a lot of materials to play with, and by doing that, you can make very different membranes. And you see here we have hollow fiber, right? Hollow fiber membrane. We have the flat membrane, different configurations. All right. So for water treatment, how can we use membrane separation? We can separate different substances from water, starting from the very large substances, the particle like sand, right? But for sand, we typically do not use membrane to separate. What do we do? How we separate sand particles from water? Filtration. We can use sedimentation, right? Sedimentation. So the particles settle by themselves because they're heavy, right? For smaller substances, we could use membrane separation. For example, bacteria, right? Bacteria we mentioned they have a size of few micrometer, and here we can use microfiltration, right? Microfiltration or some yeast or cells, right? Cells. So you can see here to separate them. We do that not only in water treatment, right? Drug purification, right? In medical field. Then protein or virus, right? They are in the dozens or hundreds of nanometer scale. So we can use ultrafiltration. Ultrafiltration. What's the typical size of virus? What is the size of SARS-CoV-2 virus? I don't know. It's around 120 nanometer, right? 120 nanometer. It depends on how much water molecules on its surface, right? If you have many water molecules, the size will be larger. When it is in its dry state, the size could be kind of small, but overall 120 nanometer, right? So how small is this 120? What is the thickness of our hair? It's around 50 micrometer, right? And right, to think how large the virus is. So virus very small, and we can use ultrafiltration, right? But very tight ultrafiltration to remove viruses from water, right? So we have viruses in water, okay? Even drinking water, right? So our purpose is to remove these waterborne pathogens, right? Then even smaller, some molecules, right? Some molecules, sugar molecules, like the drugs you take, right? Or the hand washing solution, disinfectant, right? We can use nanofiltration, and finally reverse osmosis to remove salts, right? Say water desalination, that's reverse osmosis. And in many cases, we combine these technologies. For example, we combine ultrafiltration with reverse osmosis, right? So ultrafiltration serves as pre-treatment. Reverse osmosis is the purpose, right? We also combine conventional treatment process. For example, after coagulation, flocculation, sedimentation, we have ultrafiltration, right? So this is the concept of treatment process trend, right? So you can adjust different treatment steps to achieve your goal. Right? From microfiltration to reverse osmosis, the pore size becomes smaller and smaller, right? Smaller and smaller, and based on that, you can separate the different substances, right? Then a natural question you may ask: why don't we use reverse osmosis directly? Because it can filter out everything. why bother using microfiltration or ultrafiltration, right? What are reasons? First, it depends on how we use the water, right? If you use RO, you will get ultra pure water. But in many cases, you do not need not high quality. Toilet flushing, road washing, irrigation, right? You don't need. Secondly, of course, reverse osmosis is very expensive, right? And then you cannot send the water to RO, as we mentioned briefly, right? The membrane will be fouled very quickly. So we cannot directly use RO, and we cannot use RO in every case. Okay, so each membrane has its own purpose and applications. Summary, we have details. So let's go through them one by one. First one, microfiltration. Right, so microfiltration, they have typically large pores. How large are the pores? From 100 nanometer to 10 micrometer. Right, 100 nanometer to 10 micrometer. So it's a broad separation range. All right. Even say when you talk about microfiltration, you could have different membranes. You could have a microfiltration membrane with a pore size of 200 nanometer. You could have a microfiltration membrane with a pore size of 10 micrometer. Right. And for these two membranes, their separation functions are very different. Right. So you can imagine. As a result, when you decide what kind of membrane you want to use, you have to look at its specifications, right? Separation mechanism, mostly size. Okay, size. That is sieving effect based on their dimensions. That is the most important mechanism, right? If the materials or substances are large, then the pore larger, they will be rejected. Okay, they will be rejected. But adsorption happens as well. Okay, adsorption could remove certain percentage of the solid. But we know that absorption, the limitation is the saturation. Right? For absorption, you have absorption sites. When all the absorption sites are occupied, it reaches saturation. Right? So what do we remove? Sediments, algae, protozoan, or large bacteria? The pressure we apply is relatively low, lower than 2 bar. Right? So typically less than 1 bar, 0.5, 1, etc. Right? So microbeads and suspended solids can be removed from water. And we do have some microfiltration membranes. Where are the samples? Membrane samples. Okay, you can take a look. Right, some coupons like this, right? And we take photos of these membrane coupons under scanning electron microscope. Right, we magnify them. This is by 23,000 times. Right? So we can see the pores. Right? And the nominal pore size is 220 nanometer. But you can see the pores. Right? So they have varied size. It's not 220 nanometer. They have different pore size. Some are large, some are small. Okay, and it's made of polymer. This is top view. Okay, top view. Right, second type is ultrafiltration. So we're moving into smaller and smaller pore size membranes. Ultra. So many ultra membranes have this hollow fiber configuration. You have seen some hollow fibers, right? Hollow fibers. Pore size 10 to 100 nanometer. Okay, 10 to 100 nanometer. For example, if you use a membrane, ultrafiltration membrane with a pore size of 20, 50 nanometer, you can remove SARS-CoV-2, right? Because they are large than the pore size. What we can separate micromolecules, large molecules, colloids, and solids with molecular weight larger than 10,000 Dalton. But still, 1 to 100 nanometer is a broad range. And within that range, you have many membranes to choose. Okay. So generally speaking, we have what we call tight ultrafiltration or loose ultrafiltration, right? Tight and loose. Applied pressure 1 to 10 bar, right? Because the pores are becoming smaller, you have to apply higher pressure, right? Because the resistance increases. You have to apply higher pressure to overcome that kind of resistance. Selectivity is based on the size and charge, right? Because the pores are becoming smaller, and the role of charge becomes more important. Okay? If you have a very large pore, the charge effect is small, right? Because electrical interaction functions within a range of a few hundred nanometer. Okay, that's a typical range. Right. Design for clarification and disinfection. Right. If you have a tight filtration membrane, ultrafiltration, you can remove all the pathogens, including virus. Right. Bacteria, a few micrometer, for sure, 100% removal. Right. So it could be used for disinfection. So in my lab, we have done some research on ultrafiltration. So what we have done, we add different nanomaterials into the membrane matrix. We have added graphene, we have added carbon nanotube. These are tiny nanomaterials. We try to improve the membrane separation performance as well as their mechanical strength. Right? So mechanical strength is also important for long-term operation. Right? Imagine a batch of membranes will be used for a couple of years, like 3 years. Right? And these membranes need to stand harsh cleaning if you use some base or acid solutions. Right? So the membranes need to be tough. So we do some research with this aspect. What else? Nanofiltration, right? So nano, much smaller, right? Ultra, micro, ultra, nano even smaller. The pore size 1 to 10, 1 to a few nanometer. Extremely small. What pressure we use? 5 to 15 bar. Okay, 5 to 15 bar. For some water filtration setups used at home, you probably will see some nanofiltration membranes. Okay, the module. If you have one at your home, you can go back and check. Separation occurs through both sieving and diffusion transport mechanism. Electrostatic interaction, very important for nanofiltration. So sometimes electrostatic interaction are more important than size. Okay. What we can use it for? Water softening. What is water softening? What is hardness? What is hardness? Right. So we reduce hardness, like calcium and magnesium, ions. Okay, ions, and dissolved organics. Small organic, a few hundred Dalton, a few hundred. Okay, and permeable to monovalent ions. Permeable, monovalent like sodium chloride, but not completely permeable. Some typical nanofiltration membranes in the market, it has certain rejection for sodium chloride, probably 40 to 70%. It's not 100% through. Okay, it's not 100. Only probably 50% through. It can also reject 40 to 60, 70% sodium chloride. Okay. And finally, the densest, the smallest pore, reverse osmosis. Right? I believe you have heard of this many times, reverse osmosis. Right. So what is reverse osmosis? First, we need to talk about forward osmosis or natural osmosis. Right. Here it shows you have two solutions. Right. Two solutions. One is dilute. The other has a very high concentration of salts. And in between, you have a membrane. What happens? Water molecules get into the brine. We call this brine, right? Solution containing salt. So this is osmosis. Osmosis because there's a osmotic pressure, right? And the brine will be diluted because water molecules coming through. Right? This is forward osmosis. What is reverse osmosis? Reverse osmosis is a reverse process. Reverse process, we want the water molecules to come out of the brine and into the clean water. Right? So that is reverse. We want to reverse this process. And how can you achieve that? You have to apply a pressure. Okay? You have to apply pressure to drive water molecules to get out of the brine and into the clean water. Right? So that is reverse process of osmosis, reverse osmosis. And this is a mechanism for seawater desalination using reverse osmosis. Okay? Right. We talk about the membranes. Right? Because you have to separate the ions. The ions are very small, right? Angstrom level. You have to use a very dense membrane, and the membrane has to stand high pressure. For example, 60 bar, right? High pressure. And we have this most popular membrane is called polyamide membrane. Polyamide. Do we have the material? So PA is polyamide. We don't have the material. Let me write down. Polyamide. Okay, polyamide is a material of this layer, the yellow. Okay, but the yellow is only illustrative purpose. Okay, in reality, it's not a yellow. Okay, it's very thin, 150, a few hundred nanometers thin, but it's super dense. Right? We make it into a thin film because we do not want it to have a very high resistance. And then we have actual filtration support, and another support, right? Another support, non-woolen backing. So in total, we have quite a few number of layers. Right? By this structure, the outer membrane can withstand high pressure. Right? But the separation function rarely occurs in the top layer, the super thin layer. Okay, super thin layer. Right? So the pore is very small. Sometimes we think it's a non-porous membrane. Right? Non-porous, no pores. High pressure, 10 to 80 bars. Right? It's a composite membrane. Composite polyamide, polysulfone, right? Non-woolen backing, like polyester support. The mechanism generally the community thinks it's solution diffusion transport. Why so solution diffusion? Water molecules soak into the upstream phase of the membrane, diffuse down the chemical potential gradient across the membrane, and dissolve from the downstream phase. Right? So here it's not a pore transport mechanism. We do not have a pore. It's first absorption. It's dissolution kind of. The water molecules dissolve into the polyamide, and then it diffuses within the polyamide. What is diffusion? All right. It's based on chemical gradient diffusion, and then desorption from the polyamide. Okay, rejects almost all ionic species. Right. Right. I'll used in more and more places. We have different manufacturers. Dow Chemical, probably the most popular products are made by them. GE, Koch, Toray from Japan, etc. Shall we take a break? Let's take a break. All right, recap. Let's continue. You have seen the coupons, right? They are very small, a few centimeters in size. They have been cut from very large membrane sheets or hollow fibers, right? And these sheets or fibers need to be configured into a module, okay, for use. For example, here, hollow fiber module, right? So it has a module like this, and within the module, you have thousands of hollow fibers, And here you have a in it, water in it, you have water out in it, okay? We do have some photo here. Right? These are hollow fiber. This is enlarged picture, right? Hollow fiber, and this is the we call it the lumen. This is not the pore, okay? Not the pore for separation. The pores are on the surface. Okay. And within this column, we have thousands of this type of hollow fibers, right? Hollow fiber. We could have this spiral wound, right? So we wrap membrane sheets around the permeate tube, right? And we could have this flat sheet module, or this tubular module. We have some photos here, right? Flat sheet module, tubular, hollow fiber, okay, hollow fiber membrane. The thousands of these fibers are arranged. Right. So the purpose is to achieve high surface filtration surface area. Right. You can imagine how much water you can treat is proportional to the surface area, right? To the surface area. And for hollow fiber and for this spiral one, we can achieve very high packing density. Right. Within one module, you have a very high surface area. Okay, does that make sense? Right. So all this hollow fiber surface is the filtration area. Right. So here, spiral one, you have layers of membranes, multiple layers, and each layer could be used for filtration. For this spiral one configuration, you have very high surface area, right? And for this hollow fiber, typically for ultra and microfiltration. For spiral one, reverse osmosis or nanofiltration, right? Nanofiltration. Ultra filtration, microfiltration, why we have this configuration? Ultra, micro, we also do backwashing, right? Imagine this hollow fiber, right? Hollow fiber, you can do backwashing. But for reverse osmosis and nanofiltration, we do not do backwashing. Why? Why? Smaller than water? No, it's not smaller than water because it's very dense. Imagine a dense membrane. How can you pump permeate in the reverse direction to wash the membrane, right? You cannot. We cannot do backwashing for RO and nanofiltration. But for ultra and micro, we can. We can have the reverse flow, water flow. We can wash off the deposited particles. Right. Hollow fiber. Look at this. This is the module within thousands of fibers, and each fiber is like this. We could have two ways of water filtration. One is inside out. The feed water is in the, we call this lumen. Okay. Let me write down this word. Lumen. We call this. Right. Inside. And then the permeate comes out. Right. So this is inside out. So your filtration happens where? Interior surface, right? Interior surface. For outside in, right? This is feed water. This is permeate water, product water. So this is outside in. Your filtration happens at exterior surface, right? Exterior surface. Inside out, outside in. And you have seen we have some hollow fibers, right? So very tiny in diameter, right? So membrane separation is expandable. You can add module by module. Therefore, you can increase the treatment capacity. That can be easily achieved. When we talk about membrane system comprises a number of membrane banks. Right? Each membrane bank consists of a number of membrane modules, and each membrane module is an assembly of membrane elements. And the operation membrane elements and modules are parallel and independent. Right? So they are reliable. Number of membrane elements and modules can be easily increased or decreased. So we can increase the capacity in a faster manner in the easy installation of membrane. All right. I shared one article to you, uploaded in the Blackboard. It's about TKO desalination plant. Right. So please read the article. You can find from the article that installation of the RO membranes at the TKO desalination plant was completed within 10 days because it has been already pre-assembled, right? Pre-assembled. So easy installation and easy maintenance and replacement of membrane module. If one module fails to function, you can replace that, right? This is the actual, right? Actual system. Look at this, right? Of course, you have different configurations, different height, different diameter, right? Which suggests different filtration areas or different water production capacity, right? Operation mode. This is with regard to the membrane surface, right? no matter it's hollow fiber or it's a flat membrane, you have a surface, right? Then the water flow could be in a perpendicular direction to the membrane surface. We call this dead end. Okay, we call this dead end filtration, perpendicular. Right. So this is more relevant to micro and ultrafiltration. Dead end filtration. We could also have we call this cross flow. Cross flow. The water flow direction is in parallel direction to the membrane surface. Okay, so parallel. This is cross flow. But still, you have a pressure in this direction, right? So the water molecules can get through. Right, get through. For dead end on the surface, you have homogeneous water distribution. But for cross flow, at the front end, you will have higher water flow, right? At the end, you will have lower flow because here you'll have higher concentration of solute. You are concentrating the flow along the direction, okay, along the direction. So we use cross flow in microfiltration or in nanofiltration or reverse osmosis. Okay, reverse osmosis. So dead end filtration flow causes build up the filter cake, right? So this is membrane fouling. It's avoided in cross flow, not avoided, mitigated. Okay, it's not 100% avoidance of the problem. Still, you will have fouling, okay, but a reduced condition. So this is the operation mode. Another concept, a very important concept, is concentration polarization. Okay, so this concept, what is the concept? Imagine you have a membrane surface here. You are pushing the flow, right, to the surface, and water molecules get through the pores, but not the solutes. So you will have very high concentration of solutes near the membrane surface. Okay, so here the buildup of solutes, the concentration is much higher than in the bulk phase, in the bulk water. So this is called concentration polarization. Okay, concentration polarization is a reversible process. Okay, reversible process. When you release the pressure, they will move into the bulk phase, right? They will move away from the membrane surface into the bulk water. Okay, but during the operation, they are concentrated in a very thin layer near the membrane surface. So that is concentration polarization. Because of concentration gradient, you have a high concentration near the membrane surface, you have lower concentration in the bulk, there will be back diffusion, okay, back transport of the solutes. So concentration polarization makes the membrane operation somehow complicated, okay, somehow complicated. But we are not going to discuss the details about concentration polarization, but you should understand what is concentration polarization. Right? It's showing also in this schematic. You see here the solute is much higher in the bulk. So there's back diffusion, but your flow direction is still from the right to the left. Right? Osmotic pressure. Right. So concentration polarization is usually unwanted because it decreases the flux, increases the potential for fouling to occur because you have a high concentration layer. Right? So the solutes are more easily to attach on the membrane surface. That is fouling. Concentration polarization is reversible, right? You just change the flow pattern. You shut off the pressure. The solids will go back into the bulk. But concentration polarization, so it's not same as fouling. Right? It's not same as fouling. Concentration polarization occurs still in water, a layer close to the membrane surface. Okay, not on the membrane surface. Fouling happens on or in the membrane. Make sense? What's the difference? Right? So this layer is still in water, but you can imagine some solutes will come to the membrane surface. Right? That is where the fouling takes place. Right, let's talk about fouling. Fouling happens in standard filtration, in standard filter. So we use backwashing, right? We use backwashing. Fouling happens on the membrane surface. Different types, okay? Different types. In our slides, we say that the fouling is irreversible deposition or adsorption on the membrane surface or into the membrane pores. Okay, irreversible. So they cannot be changed back into the original state. Okay, but in academic research, we sometimes classify them as reversible and irreversible. Right. The reversible part means if we use some cleaning method, some foulants will be removed. Right. So that part is reversible. The irreversible part is the part which you cannot remove using even cleaning methods. Causes flux decline or higher transmission pressure, and this is understandable, right? Because they block the water transport channels and modify the retention properties of membrane. Right? Now the membrane has the properties similar to the foulants. Right? It differs from concentration polarization. This is a foul hollow fiber membrane. Right? See here, very dirty, very dirty. Right? Fouling mechanism. What kind of fouling? Narrow the pore. Right? Attached to the surface of the pore, so the pore becomes narrower. Plugging to completely block the pore. Gel formation or cake formation on top of the pore on the surface. It's like a gel and like a cake. Right? Still block the pore, but different mechanism to pore blocking. Right, we have some definitions here. It's much easier to say schematics. What are they? And different solvents. It depends on what we have in water, but generally we have 4 types of solvents. The first one is colloids, small particles, like clay particles, flux, right? Colloids. And then biological, bacteria, fungi, etc. And biological fouling is the most difficult type, right? The most difficult type to prevent and to control. Bacteria grow, right? Grow. So we have to sometimes use disinfectant, like chlorine, during membrane operation. It could be organic, like soils, surfactants, humics, organic matter. They block the membrane pores and precipitate on the surface. And scaling, precipitation of salts, minerals, calcium, aluminum, iron. Look at this picture. Right? So these are the minerals precipitated on the membrane. We have different solvents. We have different cleaning methods. Right? Different cleaning methods. So generic, we could do backwashing. We could do bubbling. Right? We could control the flow pattern. Right? Flow pattern. So one example regarding flow pattern. Sometimes you think that you want to achieve high flux, high treatment capacity, right? Shorter period, you get a lot of clean water. But the consequence is that you have the buildup of solvents very fast because you have treated much more water, right? So essentially, you have many more substances in the water. So you could have faster fouling under high flux, right? So from one aspect, you get more water within a fixed amount of time. On the other hand, you have to perform more frequent cleaning. So that is a trade-off, right? That is a trade-off. So flux operation, that is the meaning of controlled flux operation. For proteins, right? For proteins, we could make the membrane more hydrophilic, so they cannot easily attach, right? Clutch. For colloids, we remove these small particles ahead of membrane separation. That is pre-treatment. Okay, pre-treatment. For example, we use coagulation. We remove them first. We do not let colloids into the membrane filtration process. Okay, so pre-treatment is critical for membrane separation. Okay, biological. Sometimes we do disinfection first. So we disinfect the filtered water to the membrane. So the microorganisms can be inactivated before they get into the membrane system. Right? Imagine if they get into our RO system, they grow within the module, it becomes very difficult for you to remove them. Right? So it's better for you to do that ahead of membrane separation. Right? For different solvents, we have different methods, cleaning methods or control methods. For organics, right? We remove them first by oxidation, for example, ozone, right? For inorganics, calcium, silica, etc., we add anti-scalant. Right. So all this, not all, some of this are what we are doing in my lab. We're doing some research on this, right? How to investigate fouling and what methods we can use to control or reduce membrane fouling, right? Because you can imagine there are so many types of substances in water, different water filtration conditions, different membranes. The problems could be very complicated, and we should investigate the reasons for the problems to happen and develop methods to reduce or prevent the fouling problems. This is a flux history with fouling. Basically, you will see the flux decrease if you apply constant pressure. Okay, and different stages and correspond to different phenomena. Okay, different reasons. So what are the consequences of fouling? Increase the resistance of the membrane over time. Right, permeable flux would decline. You see lower water flux, and transmembrane pressure drops down. To increase membrane permeable flux, you have to increase the pressure. Right, you give a higher driving force because the resistance becomes higher. What's the consequence of increased pressure? How we supply pressure? How we supply pressure for membrane separation? No, pumping, right? Pumping. We use pumps. Energy consumption. So that's energy consumption. So backwashing, physical cleaning, but this applied for ultrafiltration, microfiltration, okay, not nanofiltration or reverse osmosis. Similar to standard filtration, right? You can apply air bubbling during backwashing. Or chemical cleaning. If you have scales, use acid. If you have protein, you use base. Right? Biofilms use disinfectant. Hydrophobic species use detergents. Okay, detergents. Okay. So when to initiate backwashing? When you have observed severe fouling, right? Like flux decline, transmembrane pressure increases. How to do backwashing? Very similar to backwashing in standard filtration. You apply pressurized water or air, right, into the surface or to the surface of the membrane. Reverse direction. For example, for hollow fiber membrane, if you filtration is inside out, for backwashing it should be outside in. Okay, outside in. Reverse flow, and also with higher flow rate, right? What is the backwash frequency? A few hours to days, depending on water quality and conditions. Right. Okay, so this schematic shows the backwashing. This is forward flow, right? This is backwashing. The flow is reversed, so you can wash off the foulings on the surface or in the membrane pores. we cannot wait for the membrane fouling to happen and then clean. We have to prevent fouling. So pre-treatment is the first thing you should do. Pre-treatment, right? And then cleaning, cleaning. Also important system operating pressure and recovery, right? And use membranes with improved or desired properties, different membranes, right? Different membranes. And then use disinfectant to control biofouling. Use anti-scalant to control precipitation of salts. All right. Any questions so far? No. No question. I think we should take a short break. Then we move to our design. Right? Take a short break. All right, so let's continue. Let me talk a little more about different operation modes. We have introduced the two modes, right? The first one is dead end. Dead end. This is membrane surface. You have the fade, and you have the pyramid. All right, fade and pyramid. That's very straightforward to understand, right? But for cross flow, here is your fade, right? This is membrane surface. Where is your pyramid? Right, so vertical. This is pyramid. But you see here, the water still travels along this direction. So we have retentate. Right. So for cross flow, we have this is in, but we have two outside. Okay, two outflow. One is retentate, one is pyramid. Of course, pyramid you have clean water, but for retentate you have concentrated solution. Right. So that is separation. You have concentrated retentate. Okay, and that happens for reverse osmosis. Right, reverse osmosis. For seawater desalination, we call this the retentate, sometimes brine. Right. Very high concentration of salts because you are concentrating seawater, and it needs to be discharged back into the sea. Okay, that is a typical operation. So based on the schematic, we have this. We consider reverse osmosis membrane here. Therefore, you have fade, you have retentate, you have pyramid. Okay, three streams. And here are a number of design parameters you should pay attention to. The first one is transmembrane pressure. Okay, TMP, transmembrane pressure. The pressure, the driving force. Okay, driving force. Yield, how much water you can recover. What's the percentage, right? Yield. Rejection, that's easy to understand. If you have 10 gram per liter, say salts. This is just one example. In the permeate, it's 1 gram. What is the rejection? From 10 to 1. Rejection 90%, right? The rejection 90%. Transmembrane flux. Flux is how much water you get. Permeate flow rate Q. And total membrane surface required A. Let's look at the first parameter, transmembrane pressure. Transmembrane pressure. Is pressure differential from the fade side to the permeate side? Right. Fade side you have pressure, permeate side you have pressure, and that's the difference between the two sides. The net pressure acting on the membrane on the feed side is the feed pressure minus osmotic pressure of the feed side. Right, so we have a concept here, osmotic pressure. Osmotic pressure, because I have salty water. Right? Imagine the forward osmosis process. Right? So there you have osmotic pressure. And you have to overcome that pressure to get water molecules. The osmotic pressure. And this is on the feed side. On the permeate side, you have the permeate side pressure and osmotic pressure of the permeate. Osmotic pressure of permeate. And the difference, feed side minus permeate side, right? Is actually delta P minus delta pi. Okay, delta P minus delta pi. And how can we calculate osmotic pressure? We have an equation, Van Hoff equation. This is very similar to ideal gas law. When you look at the equation very carefully, right? Concentration, right? Molar concentration of all solutes. For example, for sodium chloride in seawater, you need to consider both sodium and chlorine ion, all ions, molar concentration, and times R gas constant, right? Gas constant, and temperature, absolute temperature, Kelvin, right? Kelvin. For dilute solutions, pi is negligible because here the C is very small. The osmotic pressure is almost 0. But for our seawater, salty water, you cannot ignore. Okay, you cannot ignore. You have to consider the delta P pressure net equals delta P minus 0 is delta P here for dilute solution. Right? For example, our surface water, right? Surface water, river water. The osmotic pressure is very low if you calculate. For concentrated solution like seawater, pi is not negligible. Net applied pressure is delta P minus delta pi. Right. Here is one example. Okay, 0.1 mole sodium chloride. What is the osmotic pressure? Right, 0.1 mole. So we use the Van Hoff equation. We have first calculated the molar concentration of all solutes. But all solutes means both cations and ions, right? Sodium and chlorine. Therefore, here we apply 2, right? Because you have 1 sodium, you have 1 chlorine, and minus 2. That's 2. And then the water density. So therefore, it's 0.2 mole, 2 mole, and the volume. Okay, we change this to cubic meter. Okay, so this is liter. We change liter into cubic meter, and temperature 25 degrees Celsius. Right, it's 298 Kelvin, and we get 4.88 atmosphere. That's osmotic pressure, right? If you have this type of salt water, you want to do seawater desalination, you have to apply pressure higher than this. Otherwise, you will not be successful. Okay, you will not be successful. Experimental value is about 4.56. Okay, 4.56. So I think we have some time. Let's do one example. Let's calculate this 3.45 weight percent. Okay, so this is weight percent. You have to convert weight percent into molar. This is seawater, typical seawater. So we'll get a number close to 25 atmosphere. What does weight percent mean? Weight percent, 3.45, right? 34.5 gram per liter. That is the concentration. Okay, so please try to calculate osmotic pressure of seawater. 25 degree Celsius. Did you get a number close to 25? What is the number you get? Huh? How much you get? Right? You have to do time 2 and 0.082, right? ATM, atmosphere times liter per mole per Kelvin times 298 Kelvin. Huh? 28.8. I don't know. I didn't check. He said 28.8. Just check the answer. Right? But the procedure is the same. Right, just here. Not very difficult. So double check the number. In reality, the measurement 25 atmosphere. So that is a threshold pressure. Okay. If you apply a pressure lower than 25, you will not get water. Okay, you have to overcome that pressure barrier. So in reality, what's the pressure we use at TKO desalination plant? Anyone knows? It's around 60, 60, right? So almost double the pressure. Question? Okay. So you know this number, right? 58.5. Everyone knows what is 58.5? Do you know this number? Molecular weight, sodium chloride. Okay, molecular weight of sodium chloride. Basically, we are converting the mass concentration into mole concentration. Because here it's mole concentration, molar concentration. All right? Okay. That is the pressure. Let me emphasize again. That's the pressure you have to overcome. You have to apply a pressure higher than that for seawater desalination. Okay. So in reality, we applied 50, 60, sometimes even higher pressure, much higher than osmotic pressure, to drive the process. Okay, to drive the process. Okay. Another concept is yield. Yield is how much water you recover from seawater. For example, if you send in 1 cubic meter into the RO, you get 0.5 cubic meter of clean water. Yield is 50%, right? 50%. That's 0.5. Rejection, that's easy. Concentration, right? The difference, 1 minus C concentration in the permeant over the concentration in the feed, all right? For state of the art, RO, sodium chloride rejection, 99.9. Okay, very efficient, very efficient. It is actually so efficient, we have to add minerals back into the product water, right? So at chunking off desalination plant, we have a post-treatment step. You add useful minerals, magnesium, fluoride, right? Fluoride is very important for our bones, for teeth, right? So you have to add these minerals back into the water. Okay, and typically you can find all the information from the membrane specifications. Operation range, applied pressure range, the yield, rejection for different sorts. Okay, different sorts. And transmembrane flux, J, into permeable flow rate over total membrane surface area. It also equals transmembrane pressure over resistance. Okay, resistance. And transmembrane pressure delta P net, right? Divided by mu viscosity of fluid times the sum of all non-negligible form of resistance. Right. So here we have only the equations, but in reality we calculate the total resistance. Okay, the resistance from, for example, from the membrane itself, from the fouling layer, etc. Right, you have different components of the resistance, and we study different components. Right here, polarization layer resistance, external fouling resistance, internal resistance, and membrane resistance. Right. So our total is a summation of all this. I'm going to skip this anyway. Schematic showing the different types or different sources of resistance. Right. And system permeable flow. This equation is important for our design of a membrane separation plant. J is transmembrane flux. Look at its unit. It's liter per square meter per hour. Okay. A is total effective membrane surface area square meter unit. So you get a Q. The unit is liter per hour. Right. How many liters of water you can produce within 1 hour? So that is capacity. Right. So that is capacity. If you have a desired capacity, right, you have transmembrane flux. This is usually given for a certain type of membrane. You can calculate how much membrane surface area you need. Right. So that is the design. A very simple philosophy there. QP is given. Right. QP is given. For TKO, it's the first phase. Anyone knows what's the capacity? TKO. Correct me if I'm wrong. This is the right. It's 135,000 cubic meters per day, and that is QP. That is capacity. Right. If you know J, you can calculate the area you need, and for each membrane module, it has certain filtration area, right? So you can know how many modules you need. But that's of course, that's a very simple math. But in reality, it should be more complicated. You have to consider uncertainty, whatever, right? Right. Area QP divided by J. QP divided by J. Right. According to the surface area, number of membrane element modules and banks can be determined. Okay. And this number is 5%, right? 5% of our daily clean water use in Hong Kong. The times that number by 20 is the total amount of water we use. Right. Very briefly, membrane. Where we can use membrane in water treatment. Right. So this is, you know this, right? This is exactly what we have learned in the previous lecture. Coagulation, fluctuations. What is this? Sedimentation, right? Sedimentation, sanitary filtration. Next lecture we're going to learn disinfection, and this is storage, then distribution, like a reservoir, right? Reservoir. And a very simple application for membrane is to replace sand filter with filtration, membrane filtration. Okay, sand filtration. So in certain places, arterial filtration is added after sand filtration, but in some places, sand filter has been completely replaced. Right, so you can use arterial filtration here, or even nanofiltration. Right. So people are talking about using nanofiltration. So in Shanghai and some other cities, some newest built water treatment plants are using nanofiltration. Okay. Of course, it will be more expensive. Right. One is membrane modules. Look at the membrane modules. Right. And sand. Right. Sand particles, they're cheap. Right. But you get higher reliability, higher water quality. Okay. Higher water quality. And you can use less disinfectant, which will introduce coming lecture about disinfection. But this is one example where membrane can be used for you to get higher water quality. Okay, to upgrade conventional water treatment. Okay, so our very last topic is about RO, seawater desalination. Our classic example is a chunking out desalination plant. Right, so it costs a lot of money, right? 10 billion Hong Kong dollars for the first phase. It has been commissioned last December. So perhaps some of you are already drinking the water from that plant. All right. It had different facilities, right, including the district building types, the plants, etc. 5% of the production. Right. So this is the photo of the plant. It's nearby the landfill. Um, membrane modules. Intake from here. Outflow is like here, right? So the brain, the concentrate. Uh, um, so this is our modules, many modules. But not only our. We said you cannot send water directly into our, right? So before that, there's a step called DAF. We didn't talk about DAF. Very interestingly, so in Hong Kong, we do not use actual filtration as a right. So it's dissolved air flotation, I guess. Dissolved air flotation, right? DAF. So in many other places, actual filtration or microfiltration is used as a pretreatment for RO. Right? But in Hong Kong, we have this DAF process. The DAF is exactly the reverse of sedimentation. Right? So sedimentation, you have particles settle naturally to the bottom of the tank, right? But for DAF, you have air bubble from the bottom, which brings the particles to the top water surface, and then all these substances are scraped off, right? So this is used for substances with low density, right? With low density, because they are light, it's more difficult for you to settle them than float them, right? Float them. So perhaps our source water, say water, has more lighter materials, right? So DAF is used to remove these substances before sending them into RO. Okay. Right. A large plant is probably one of the largest in the world, and it could be expanded and with a double size, 270,000 cubic meter per day. That will be 10% of our water use in the future. Okay. Any question? No. Not at all. Okay. I have uploaded the article. Please read. Okay. It's from HKIE journal. I think it's a very interesting article to read about DKO desalination plant. So I would say it's one of the most advanced water treatment facilities in the world, right? Most advanced technology, and some other very interesting feature like energy saving, energy recovery. In our very important, because you see we are using 60 bar, right? Applied pressure. So some devices have been developed and are being used to recover energy from the concentrate, right? So the modern our plant can be run very efficiently, actually, very efficiently. Some studies say our process is approaching the thermodynamic limit, right? It's a very efficient process. Right, so please read that article. We do not have a lot of calculations for this part because the calculation could be very difficult, could be very complicated when you look at the microscale transport phenomenon, right? It's much more complicated. So we have only very simple, very high level understanding of membrane separation. So for this part, you have to know a lot of concepts. Okay, different types of membrane separation. That is a must, right? Micro, ultra, nano, RO. What are the features, and what can we use them for? And some basic concepts like concentration polarization, fouling, backwashing, recovery yield, rejection, permeability, right? Different types of foulants, and what methods can we use to clean different types of foulants, right? A lot of concepts for today's lecture. Okay, so I'll give you some time for you to go home early to read the article. Okay, okay, I'll see you next week.